Well, I guess nobody wants that to happen at their power station. I don't know if you've ever witnessed such a dramatic event as a rotor stator, but fortunately they don't happen very often. But when they do, they're quite spectacular and noisy.
In February 1999, after 4 years of construction, Salto Caxias hydroelectric plant, installed on Iguazu River, Brazil, is about to commission 4 units of 310 megawatts each, with the promise to provide electricity to 4 million people, roughly 40% of Paraná's population. At that time, no one suspected that a catastrophic failure could be imminent.
So they had 4 units at this power station. They were building them. And the OEM that won the bid had a new design. Well, at that time, it was a new design. And the design just simply was that the rotor rim, it was actually a shrink fit rim. But if the unit ever went beyond 110% speed, the rim would be allowed to move around, what we call floating around, to absorb the centrifugal forces.
The utility accepted the bid on the condition that the OEM would be able to validate or confirm the performance of the rotor rim to make sure it performed as designed. To do so, they installed 16 airgap sensors on all 4 units, 8 at the upper part and 8 at the bottom part, to look at the rotor and see how it behaves during overspeeds.
When I got there for this particular visit, they had done some initial testing. And that was prior to the commissioning. And in fact, we could see that some coaxial cables were already ripped off. They were actually clipped by the rotor. In reality, for the cables to be clipped, something needed to be at a distance less than 3 millimeters from the core, because the cables are very small. And to be able to rip a cable off, it needs to be at least 3 millimeters close to the stator. So in reality, in the end, they found some interconnections, pole interconnections, that were actually damaged. So they were very close to hitting the stator core.
That was the first indication there was a potential issue with the rotor. When they were ready to begin the commissioning, the utility wanted to do a controlled overspeed test to make sure the rotor performed correctly.
Overspeed condition is something that hydro generators can be expected to go through at any time. If they're producing power and for some reason they get disconnected from the grid, they'll go into overspeed, and the OEM has to show that the unit is able to survive this. So they did a controlled overspeed test, and at the same time they wanted to use the results to see if the rotor rim actually performed as the OEM had designed. They did it was quite fast. I think they went up to 154% speed, which is very fast for large units like this. And we took the readings during that test and we started to analyze the results. And if you looked at the graph, you could see that the air gap during the overspeed was much smaller than the design. The design was 19 millimeters and the results were around 14 millimeters. So the air gap during this test was much smaller, but that's to be expected. Again, the excessive centrifugal forces caused the rotor to increase in size, so therefore the air gap is smaller. And in addition, we could see that the rotor shape, the rotor circularity, was very high, was in fact beyond critical. And again, that's also to be expected because that's the design of the rotor. The rotor is moving, it's distorting to absorb the centrifugal forces, so you expect to see a shape that is distorted. And as they slow the unit down, you can see the air gap increase because the rotor is slowly shrinking in size. There's less and less centrifugal forces, so the rotor is decreasing in size. And also, it's moving less and less. So the rotor circularity, its rotor shape, was actually also improving.
If you look at the initial results, everything looked like the unit performed as designed. Everybody thought that the rotor rim was actually doing what it was supposed to.
Although it seemed to be doing what it was supposed to, it was in fact going back to a shrink fit. But the issue was that it was doing so at a speed that was way too slow.
These particular units were designed to allow the rotor rim to float as the speed reached 110% of the nominal speed during an overspeed or a load rejection event. In this case, the nominal speed was 90 RPM, so 110% speed was 99 RPM.
But in fact, not only did it miss the 99 RPM target, it also missed the 90 RPM target, which is the nominal speed.
The rim went back to its original shape or position at 80 RPM. If the unit was operating at full load, there would be tremendous heat, tremendous electromagnetic forces produced by the rotor, and tremendous electromagnetic forces produced by the stator. With these results in mind, and at that operating condition, it isn't hard to imagine the rim starting to float. Obviously, that would have been catastrophic. The rotor rim would have been pulled off and the stator would have been destroyed. The results were analyzed and the OEM went back to the drawing board. They increased the constraints for the rotor rim. They wanted to make sure the rim would start to float at a higher speed, therefore avoiding that 90 RPM limit. The modifications were performed by the OEM and tests were conducted. Fortunately, the rotor performed flawlessly. If that problem had been left unchecked, the utility might have had 4 major rotor stator ruptures, causing tremendous amounts of damage. VibroSystM's air gap monitoring system, commonly known as AGMS, helped the utility and the OEM solve these issues and prevent any damages. As testified by the customer, the repairs and verification using the AGMS saved significant time and costs. The new method should be adopted in the future since it detects problems before the commercial operation of the units. Test results comparison is made before and after corrective action, showing the AGMS ability to detect the problem and to confirm the repair effectiveness.
To me, that was a very good case of everybody working together to solve a problem. It was a very interesting case. It was a very eye-opening case because I could see how you can use the information from such a system and learn a great deal, be able to assess, analyze, and correct a problem very easily. Well, good morning, everybody. Thank you so much for joining us this morning. My name is André Tétrault, and I am the Director of the Test and Diagnostics Department here at VibroSystM. As usual, I'm joined by my colleague, Mr. Paul Amelinks. As you know, Paul is one of our analysts here at the Test and Diagnostics Department. He will be, as usual, handling all the logistics, handling the screens, the questions, and also will be handling any and all questions in Spanish or Portuguese. So for our Latin American friends, get your questions ready. We'll do our best to answer them. So Paul, good morning.
Morning. Buenos dias, bon dia. Thank you, André. Hello, everyone. Buen dia a todos. Welcome to this Q&A session. For our friends in Latin America, Spain, Brazil, and Portugal, please feel free to submit your questions in Spanish or Portuguese. We will be glad to answer them as well. Muy buen día a todos y bienvenidos a esta sesión de preguntas y respuestas para nuestros amigos de América Latina, España, Brasil y Portugal. Ustedes bien pueden formular sus preguntas en español o portugués, las que responderemos con mucho gusto. Hoy presentamos un caso de estudio ocurrido en la central hidroeléctrica Salto Caxias, que es servida por el río Iguazú en el estado de Paraná, Brasil. Com muito prazer para os nossos amigos do Brasil.
So welcome to our 10th Q&A session live on YouTube directly from our beautiful head office here in Montreal, Quebec, Canada. I am very happy to be here with you to discuss, that nice little video we had for you this morning, and also any other topics you'd like to discuss. We're very excited this morning because, as you can see, we're kicking off our new Q&A session series. This one is called Catastrophes Avoided or Not.
Or not.
Evidently, one of the major reasons that monitoring systems are implemented, of course, is to avoid tremendous catastrophes. But preventing catastrophes are not that common. They're not uncommon either, but they don't happen that often. So to show you some of the do's and don'ts that can occur at power stations, I've chosen some interesting cases that we've been involved with over the years. One specific case, as you saw this morning, was a case that I was involved in South America many years ago. So we will be covering different events, different incidents that occurred throughout our careers, I guess, and to show you how you can avoid some catastrophes or at least understand what happened at your power plant. So, Paul?
Remember that to be able to submit your questions during this Q&A session, you would need to log on with your YouTube account. As mentioned previously in our Q sessions, we want to make sure that all questions asked previously are answered today. We will answer today's questions at the end of the session if we have time. Recuerde que para poder enviar sus preguntas durante esta sesión, usted necesita ingresar con su cuenta YouTube. Tal como hemos mencionado en anteriores oportunidades, nuestro objetivo es que todas sus preguntas anteriores sean respondidas durante esta sesión. El día de hoy trataremos de responder todas las preguntas al final de la sesión que hayan sido formuladas el día de hoy, si tenemos tiempo.
So I hope you enjoyed our little video this morning. It brings back memories for me because this particular case, I had a very privileged view because I was the field engineer on site to do all the testing at that time. And in reality, I was there for two reasons. The first, of course, was to commission our system and then commission their units, not all four of them because the power station was being built at the time. So the case that you saw was on unit number 2. And also, for those who are old enough, like Paul and I was there to make sure the system was able to go through the Y2K crisis. For those of you who remember that, it was a big deal. For those who are younger, you have no idea what I'm talking about. So I was there to make sure everything was working. And then while I was there, we did some testing. And as you could see, there were some issues.
That was before the smartphones.
Yeah, way before the smartphones. There were some issues on this unit. And as I mentioned in the video, it was very interesting for me because I was a field engineer at the time. And installing this equipment, doing the commissionings and testing, we have access to a tremendous amount of data, air gap data, rotor stator dynamics, shaft vibration, temperature, flux, axial displacement, turbine movement, acceleration. There's all kinds of parameters that we can monitor. And as I moved on in my career, I had more and more incidents where you could see how the system was able to detect very small anomalies and be able to provide critical information for managing these assets. As I mention often in my training courses, although people expect the air gap monitoring system to see a pole sticking out, like 5 millimeters, but in reality, that happens very, very doesn't happen very often. You're usually looking at small details, and although the case we showed you this morning was in fact a critical situation. The data, unless you had expertise or paid close attention to the results, it was very difficult to see the problem. And luckily for me, I was curious enough and had enough experience to understand what the design for the rotor was, to look into the results in more detail and take a situation where people felt the unit actually performed as it was supposed to going to a case where the unit was in trouble and the unit was not performing as it was supposed to with a small difference. But that small difference could have made the difference or would have made the difference between a unit that's working correctly and a catastrophic event. So it was very enlightening for me to be able to discuss with the OEM, to discuss with the utility, look at the findings, understand what was going on, raising everybody's eyebrows, going, whoa, okay, we have a serious problem here, and letting them go back to their drawing board and come up with some better constraints, apply those constraints, redo the tests, and find out that the units were now working correctly. And as I mentioned in the video, these units have been working since 1999 flawlessly as far as we know. So, information is power. When you have these systems, yes, you can use them as protection systems. They have all the protection relays and information that you need. But if you do take the time to sit down and look at the data, learn what to look for, learn how to look at those results, compare them to existing tolerances, and be in a much better position to understand how the units are performing, and being able to plan outages, make slight modifications to ensure the long-term operating condition of the unit, instead of waiting for a catastrophe and then having to spend millions of dollars to fix it. So I hope you have some questions for us today. I have some slides if some people want a little more explanation on how I was able to show that the unit had an issue. And we'll show you that on our slides. But Paul, do we have any questions?
Yeah, thank you, Andre. That was very interesting. We do have some questions here.
Okay.
Let me bring some up. The first one: is this a problem we can detect with only one sensor? I mean, one air gap sensor?
Yes. Yeah, you could detect a rotor rim issue with one sensor, but you are somewhat limited. For example, if the unit that we saw there, the issue was not just on the top sensor, but on the bottom sensor. So the rotor at the top and at the bottom were having the same issue. So if you look at the top and you see some problems, they may not exist at the bottom, and vice versa. You might see something at the bottom that you may not see at the top. And in fact, there's another big power station in South America where the rotors were very, very tall. I think they were above 3 meters. And they suspected that the smallest air gap was not at the top nor at the bottom, but actually at the middle. So we installed top sensors, bottom sensors, and middle sensors. And when we did testing, it showed they were absolutely correct. The poles were actually convex, which means that they were sort of bending outwards at the middle instead of at the top and the bottom. So if you look at the top and at the bottom, you're actually not seeing the minimum air gap. And if you have a small air gap, you're going to completely miss that part of it. So yes, you can look at rotor movement using one air gap sensor. If you have a tall rotor, we strongly recommend that you put top and bottom. But if you're going to put sensors in to look at a problem with the rotor, why not just put sensors all the way around like they did, and have a chance to not only look at the rotor, but also look at the stator. And there's a lot of dynamics involved between the rotor and stator. There's all kinds of issues with the rotor that will cause stress to the stator, and vice versa. Stators that are out of round will create an uneven magnetic field, put tremendous amount of stress on the rotor components, and the more sensors you have, the better position you're in to look at it. Plus, the use of shaft displacement probes near the rotor can also tell you how much the rotor is moving around. So yes, you can, but it's a much better proposition to have sensors installed top and bottom and all along the circumference of the stator.
And we have another question. This time is from Stephanie Poudrette. How the OEM, the manufacturer, reacted to the results exposed by VibroSystM?
That's always a very interesting situation. In my career as a field engineer, and I'm sure all our Zoom implementation experts can relate to this. One of the things that is particular to our job is that when we show up on site to do commissioning, specifically if it's a new unit or a newly refurbished unit, the utility is there worried, the OEM is there worried, and you're in front of the computer looking at results, and you have like 15 people behind you just waiting for you to tell them what's going on. So it creates, in many cases, a very stressful, sort of bizarre environment where everybody has an agenda, everybody has hopes for what the results are going to be, and you just have to stay straightforward and just tell it like it is, regardless who is happy and who is not. In this particular case, the OEM was fantastic. The OEM, remember, this was a new design for them as well. It was not just a new design for the utility, it was a new design for them. So this was like their beta site. So for them, they took it as a fantastic opportunity to validate their design. And although it was unfortunate that the design did not function exactly as expected, they weren't that far off. I mean, the offset was critical, but they were still not very far from their objective. So they were able to take our data. They were very receptive, participated in all the discussions. There was no hesitation, no animosity. They were just taking all the data. They knew the data was precise. They knew the data was correct. And with the utility, we looked at the entire project, and they went back to the drawing board, calculated or determined what the issue was. In reality, as far as I can remember, they simply increased the constraints for the rotor rim so that the rim would start floating at a slightly higher speed and would go back to a shrink fit also at a slight higher speed to avoid remain floating at the nominal speed, or like we saw in this case, it was actually less than the nominal speed. So the OEM in this case, and I have to admit that in many cases, that's how they react. They were fantastic. They took all the data and fixed the issue. So everybody was working together in this case.
And we have another question from Ravishek Dixit from India. I think it's about midnight down there.
It's late.
Yeah. Hi, Ravishek. You're working late. Can we analyze all the problems related to airgap sensors with 4 sensors and a 30 megawatt hydro generator? Also, please elaborate the locations of sensor installation if we use total of 4 airgap sensors.
Okay, good question. The issue is not the megawatts. I know I've had many discussions with utilities or OEMs talking about how much, how many sensors, or even if sensors were pertinent, because the unit's very small, we generate only 10 megawatts, and a system, it's not a cost-efficient exercise for us to put this type of equipment with this cost on smaller units. And my response is always, well, okay, so if this unit goes down, that's not a problem for you. If it's stopped for 6 months, that's not an issue. If it isn't, then no, you don't need any monitoring, in fact. But the reaction is always, no, this unit is extremely important. It's critical to our operation. So why are we talking about megawatts? We're talking about how important is this asset to you. And if it is important, then yes, you do need monitoring. Now, if it's a small unit, maybe you won't buy a $1 million monitoring system, but you still need to have something to ensure that your unit is functioning properly, specifically if it's a brand new unit. I mean, the OEM has to validate that what they're delivering actually works as promised. You can't do that if you don't have any data whatsoever. Now, if we go back to how many sensors and locations, that's a question of geometry. The size of the unit will determine how many sensors you want to put all the way around. The larger the unit, the more sensors you need, because you want to avoid having large sections of the stator that are not being monitored. And then you go into the height. If it's a very, very small unit, it's less than 1 meter high, maybe 1 level is sufficient. The higher the rotor size, hence the stator size, the more you have to go into multiple levels of sensors, at least 2, top and bottom. And as I mentioned with the other power station, they actually used 3. So the size of the unit will determine how many sensors. The height of the unit will determine if you're using top and bottom or middle sensors. And the actual air gap will tell you which type of sensor you need. We have 3 basic types that are used. And the configuration of your system is, for the air gap, is based on actual size to make sure you have the proper coverage.
We have another question from Amir Iqbal. How we determine the quantity of air gap sensors according to the diameter of the stator?
Okay, we have a criteria. Don't hold me to this. I don't actually specify sensors, but there's a question of the diameter or the radius of the stator. I think it's above less than 6 meters in diameter. We recommend 4 at the top. If you go up to 7.5 meters, we recommend 8, and anything above 7.5 meters, we usually recommend putting 10 or 12. Again, the height will determine where, if you're going to install them on multiple levels. Like I said, anything less than 1 or 1.2 meters, we usually go for 4 at the top, and we sometimes put 1 at the bottom to get a peek at what the bottom of the rotor is doing. We can't monitor the stator with just 1, but we can look at the rotor and see if the top and bottom shapes are working together. Anything above 1.2 meters or above 1.5 meters, we start thinking of putting top and bottom on all sides, because the stators also will have a tendency to expand unevenly. We're actually working on a few power stations in South America right now where we're looking at their units, 2 units at the same power station, and the top and bottom stator shapes don't work together. They distort somewhat, and it causes all kinds of structural issues. So again, the size, anything less than 6 meters, we specify 4, sometimes 1 at the bottom. From 6 to 7.5, I believe, we go to 8. And anything above that, we go to 10 and 12. And again, less than 1 meter or less than 1.2 meters, we go at 1 level. Above that, we start thinking of putting up both levels. Anything above 3 meters, which of course is rare but exists, then we specify three different levels.
We have another question here. At the beginning of the video, you mentioned that the problem with the pole interconnections, there was a problem with the pole interconnections. Have you seen this problem elsewhere?
No, I don't remember. I'm sure it's happened somewhere else, but I don't remember a case where we had sensors that were clipped by the pole interconnections. I have seen a few places. One is in Quebec. There's another one in British Columbia. And I believe there was another case in Europe where the rotor actually would have hit the stator, was it not for our sensors. They actually ripped the face off the sensor, but the sensor still remained on the core. These things are glued with epoxy.
It was shaved.
It's extremely difficult to remove. In fact, if you have a sensor that's damaged, we recommend you leave it there and just install one adjacent to it, because removing them is difficult. You need a chisel, you need a hammer. Chances are you're going to damage the laminations. You might as well just leave it put and just put another sensor next to it. In fact, some of our business managers will tell you that we have a sensor that can protect the unit from a rotor stator rub, because the sensor takes the brunt of the pole contact. We do have a lot of pole interconnection problems that are caused by repeated cycling. You know, if you increase the heat, increase the load, the rotor will expand. It will also expand due to centrifugal forces, and that expansion and contraction, if it's repeated, will put some stress on the interpole connections, especially if they're rigid connections, which people are avoiding now. You have flexible ones now. The rigid ones don't like to expand and contract too well, and they have a tendency to fail. The flexible ones can also fail, and then when they do, it's usually progressive failure. And what happens is that the laminations will fail one after the other, and you'll have the same amount of current flowing through a material that is smaller and smaller and smaller. So that will generate heat. So we have a sensor that's an infrared sensor that you can install in ventilation holes, and you can look at the temperature of the pole interconnections and see if they're heating up. And if they are, it's an indication that you might want to take a look and see if the interconnection has an issue. So the specific problem that we discussed this morning, I have not seen another case where sensors were damaged because of the interconnection, the pole interconnection, but we see quite a few pole interconnections that have issues in that they're wearing down, and that produces an increase in the amount of heat they generate, and we can see that with the infrared sensor.
We have another question. Are rotor rim problems common? And if so, what impact do they have in the operation of the units?
Yes. I don't know if we can call them all rotor rim problems. Rotor rim anomalies are present. In some cases, the rim, well, I guess the most common thing we see, and we see hydro results on a weekly basis. We look at hundreds of machines a year. And the most common issue we see with rotor rims is that they will develop an elliptic shape after time. They will expand, north and south, and they won't go back to their original shape. So the rim actually is stressed to some extent where it will pull out north and south. And eventually it causes an issue where you need to go in there and remove the poles and re-shrink the rim properly. That was a common issue they had in the 70s and 80s, where there were a lot of floating rim designs out there. And these rotors were turned out to be such a problem that most of the utilities just permanently shrunk fit them so that they didn't do this anymore. So we see that quite often, and for the mechanical engineers, that produces a second harmonic, which is very high once the unit is energized. So you can look at the shaft, or you can look at the core and the frame, and you'll see a strong second harmonic show up on those components. Other issues we see also is a little bit of what we saw this morning, where if you bring the unit up to speed, or if you excite the unit, the rim will start to move. And in some cases, we did a report last week where they had issues at speed no load, after the field flash, and after the synchronization. The rim would float, would move around, and you can see that by looking at repetitive turns on an XY graph. And you can see that the air gap traces are not parallel. If you have 8 air gap sensors all the way around, they're looking at different parts of the rotor, but they're looking at the same rotor. So they should basically produce the same profile, because it's the same rotor. They'll have different amplitudes, but the profile will be the same. And when we look at the traces and we can see that there's crisscrossing going on, we know that that's the rim is moving around, and we can observe that and comment on it. And the power station we looked at last week, when they started producing load, that movement would disappear. So that's an issue we see also, not often, but it's not a surprise when we do see it. There's a third issue we see, it's not that often, but we see it sometimes, is what we call rotor rim vibration. If you look at each rotation, you will see that the profiles are different, but consistently they will have a similar profile at each rotation, where you can see that the rim is moving, and it's not moving, or it's not displacement, it's actually vibration. And we can also see that the system we have is precise enough that we can look at that movement. So all of these issues can cause wear and tear, and of course, if the rim becomes loose, totally loose, which was what we assumed would have happened in the case we showed you this morning, that would cause, of course, tremendous damage by having poles hit the stator core. But there are many issues that can come up as well. If you have, for example, an elliptical rotor rim, what you're doing is you're not only producing electromagnetic stress on the stator bars at 100 or 120 poles per second, but you're also introducing a smaller vibration at, like I said, 2x or second harmonic, which will create a varying magnetic field. Now, that's the best way to create wear and tear on a unit. You submit the core and the bars to high flux intensity, slightly less flux intensity, high flux intensity, slightly less flux intensity at each rotation. And that will produce a stress that will cause eventually possible stator bar vibration, wedge loosening. You might have some core looseness from the frame if it's subjected to this variation for long periods of time. During the training courses that I give, we go into detail, specific detail, what happens when the rotor's not round, what happens when the stator's not round, what happens when the rotor and the stator are not centered. These are all dynamics that can cause a whole list of problems, short-term, mid-term, and we go into that during our training courses. So some of them have a big impact, some of them don't have a big impact, but all of them should at least be identified and corrected if possible.
We have another question here.
Okay.
How can you tell if it is a rotor rim issue and not a pole attachment issue?
Okay, that's a good question. It's very easy. If you have a rotor pole attachment problem, you will see one pole, an individual pole, that will be usually protruding outwards at a greater rate than anywhere else. And that's one of the analysis that we do on our in our RRS reports. We look at the expansion of the rotor as the unit goes through all the different operating conditions, from slow speed to full speed, to excited, to synchronized, up to full load hot. Sometimes we ask for overexcitation, underexcitation, synchronous condenser mode, all these different operating conditions. And we can trace the outward slow progress of the poles. And if you have a pole that has an issue, you will see that it will move outwards at a much greater rate than the others. While if you have a rotor rim issue, it won't be a case of a pole, it will be a case of sections of the rotor that you can see are moving around. So you'll see a section of, let's say 6 poles or 4 poles on one side, 6 poles on the other side, moving in, moving out, and you can see there's a lot of movement. So it's a question of area, whereas if it's a pole attachment issue, it's a question of a pole. Paul?
Yeah.
Let me take a few seconds. I want to go back to the video, and I mentioned before, if people want to see very, very easily how we were able to determine that there is an issue with the unit in the case study, I have a graph here that I can show with the software. You can easily see what I'm talking about. Okay.
Let me bring you in just
Sure.
a sec. There you go.
Okay. What you're seeing here is one air gap sensor. This one's at the bottom. Let me show you the top. Basically, it shows the same thing. Okay. It's a copy of it. But there's so many sensors, just for comprehension, I'll just put one on the screen. Now, at this point here, the rotor's under overspeed. If I put the cursor on, you'll see that it's rotating very fast. Okay, if you look at the speed down here, that's 139 RPM. Now remember, nominal is 90, so it's 49 RPM above its normal speed, which is about 154, 155%. Now, the rim is moving here, okay? And you can see here the air gap increases. Why? Well, because they're slowing down. If I move the cursor, and if you look at the speed, you'll see the speed will go down.
How many turns are we seeing here?
100 rotations.
Okay.
Yeah, sorry. Okay, so you can see the speed is decreasing now. So if the speed decreases, obviously the centrifugal forces are decreasing as well. So the rotor will slowly decrease in size. It will slowly go back to what would be its normal size. Okay. Now remember, this design was that above 99 RPM, the rim would float. Now we can see we're above 99 RPM here. We're at 139 and it's going down, and 99 RPM is here. Okay. So at that point, the design said that it should go back to a shrink fit at that moment. Of course, not instantly, but it should quickly go back to a shrink fit at this time. But if you look here, you can see how the air gap increases at a much greater rate in this section than anywhere else. Here it's progressive, and then you see a sudden rapid change in the delta. Okay, the delta, of course, is the rotor shape. We can see how the rotor shape is slowly decreasing, but the circularity, which is the indication of distortion, remains somewhat high. And then during a couple of rotations, it actually goes back to its shrink fit.
It settles.
Yeah. And it's this result that the OEM, the utility, looked at and they go, wow, the design works. It does exactly what it's supposed to. It floats to absorb the energies to allow the rotor to go through this dramatic event. And when it slows down, it goes back to its original shape. So everybody was, giving high fives. Everybody was happy. But then I told them, well, it was supposed to do it here.
But
it was supposed to do it here. But in reality, it starts doing it about here, which is about 86 RPM. That's below the nominal speed. So the utility engineers said, well, that's totally unacceptable. I mean, if that's the case, it means that theoretically, the rim could start floating at any time in operation at full load. Now, full load, if the rim starts to float, it's going to rip apart and it's going to destroy the unit. So let me show you the polar graphs, just the same representation of this information. Let's take a look. Okay. So we have a top view here of this unit, and we have tolerances that exist for rotor circularity, concentricity, stator circularity, concentricity, and the minimum air gap. And you can see that the values are high, okay? But the unit is at fast, very quick speed here. And let me just run the player, which will show you each rotation one after the other dynamically, just to show you the evolution of the rotor shape in this particular event, okay? So you'll notice that the values will eventually decrease back to an acceptable level. So it's still high, but this is normal. This is what the unit was designed to do. And you can see the rim is moving around. Now, eventually, the values will improve. Okay. As unit slows down, we're down to 99 RPM here. You can see the unit is still floating. The values are still high. Now it's starting to improve. Okay. Now, technically, the unit has gone back to a shrink fit, which is in the acceptable range. But again, the speed shows that it's 5 RPM below the nominal. And it's 14 RPM below the design. So it functioned basically the way it was designed to. It just did not do so at the correct speed. Okay, we can go back to...
Yep.
Okay, so I wanted to show you that, just to show you how I was able to look at those results and very quickly understand that, yes, the rim goes back to its original shape, but the speed is way too slow. This is unacceptable.
We have another question here.
Sure.
Just a sec. Can data recorded by your system be used to discuss issues with the manufacturer? Are there international guidelines for utilities to use in these discussions? We have our own tolerances, basically because most people use our own. We have 35 years of experience, which is much more than anyone else, regardless whether it's an association or a competitor. So, in fact, if you look at guidelines that many people use, which is CEATI, you can go to their website. It's ceati.com or .ca. And they publish tolerances, including air gap, rotor, stator tolerances. And you will see that in their literature, they have pictures of our sensors. So their tolerances are used, but we use our own. They're similar, but ours are mostly for results dynamically, whereas CEATI, if I remember correctly, their tolerances are based on the assembly floor, unit cold, not moving. And we have 4 criteria, which corresponds to the ISO philosophy, where you always have 4 severity levels. And the idea is not to panic people. The idea is to give them some tolerances to assess where they are. You still need to interpret the data or the results based on the unit you have. Is it a brand new unit?
which you'll be much more severe. Or if it's a unit was built in the 30s, well, if it's a tank, I mean, the steel is this thick,
Yes.
you can get away with, distortions that are much greater than what we have today. Today, the units are Ferraris, so if you need, 12 millimeters of steel, guess what you're going to get? 12 millimeters of steel, not 12.2, 12. So it's much easier to have problems. Yes, the data that we provide has been used quite a few times by utilities to enforce warranty issues. We go into many of those during our training courses, although we don't mention where, we don't mention who. The idea is not to criticize utilities or OEMs. The idea of our training courses is to provide knowledge and expertise. So, I mean, all the manufacturers are doing their best to produce the best machines they can, but they're very, very complex machines. So we've been involved in quite a few cases where we provided either reports or training to utilities that was used to hold serious discussions with the OEMs to have them explain why the results were not according to standards or according to designs. And in most cases, if not all, in the end, the OEM has to go in and repair or fix the problem based on this information. So yes, I've been involved in quite a few discussions with utilities and OEMs in this regard. Yeah.
We have another question from Ravishek Dixit. Can air gap problems happen due to aging issues? Please elaborate a bit.
Aging issue?
Aging.
Yeah, of course. As I mentioned before, you can have rotors that will slowly start to become elliptical over time. We had a wonderful case. Give me a second here. We've had many cases where the initial results are horrible. Well, the best case I have is in Quebec here. We have a customer that has that is in a ZoomWatch contract with us, subscribed to our ZoomWatch service. ZoomWatch, where we periodically get data from the customer and we produce reports and we put it on a web-based platform for those who want to go and take a look. I invite you to type zoomwatch.com on your computer, and you'll see there are demos available for you to look at. And these people can go to the website and look at periodic results and actually trend the performance of their units. And it also comes with a alarm service, which we used yesterday. One of our customers had some alarms on the Stator
Precisely.
core, and we're reassuring him that the problem is not a serious problem. We had a case in Quebec where the unit was fairly old, and they had some turbine issues, turbine damage. So the unit was completely pulled apart to make the repairs. And while doing so, the rotor was on the assembly floor, and they contacted a consultant to come in and inspect it, the shape, the configuration, the structure, any signs of dusting, greasing, cracking, stuff like that. And during their test, they found that the rotor was significantly elliptical, and strongly recommended that the rim be reshrunk because it was going to cause all kinds of issues, which I agree. Had I had no information whatsoever, I would have come to the same conclusion. But this customer said, well, we have a contract with VibroSystM, and they've been taking data on our units for a very long time. So why don't we ask them what they think before we take the rotor apart? Because that would have been at least 2 months additional outage, plus the cost of repairing all that. So they asked us to check and see if this was an issue. And it turned out that we had data on this unit way back until 1999. And we were able to quickly show them that, yes, the rotor shape is horrible, but it has not changed for over 20 years. So our guess is that you can run this unit safely. It's been running like this for 20 years. So this utility was able to just put the machine back online. It's been running for 3 years now, and it's fine. So sometimes the results are horrible, but if the unit is very old, there's been no damage, nothing has been observed, you can get away with those results.
It's just a little doggy
Yeah, yeah, it is horrible. It was way beyond critical tolerances for rotor circularity. But again, it was very stiff. It was elliptical, but it was not moving. Nothing was evolving. Nothing was going on. So we recommended they leave it. And I mean, if they fix it, it's not an error to fix it, but it was not required to protect the unit. We have quite a few issues of older units where the tolerances, again, that we apply are based on the age of the unit. Again, very old units have very, very thick steel. Everything is over-designed, over-manufactured. You can get away with much more than today. Today, if you have a small issue of a stator shape, of a stator expansion, of rotor shape, of shaft vibration, any of these can quickly become critical and can cause damage to new units because they are at the limit of what is required for the unit to function properly. So much more stringent or much more severe on results for new units than for old units.
We have another question here.
Sure.
Do you have a case similar to the one you just have presented where damage actually occurred?
Yes. In fact, one comes to mind, which will surely be one of the case studies that we will show you later on in this series of catastrophes, or not. In this case, was both. It was a catastrophe that occurred, but another catastrophe was avoided, and it was on a bulb unit. It was a new power plant, also in Brazil, and they had bulb units, and we were able to show why one of the units had rubbed within 6 months, I believe. And we showed them by preventing another one. So I'm sure that will be a case that we will show you. It's a very interesting case. This case is also part of our training courses because it's a good indication of paying attention and looking at small details. So yes, we've had quite a few, but this particular one I'm sure will be covered in our next, not next one, but future catastrophes avoided or not episode.
We have another question here. Can this equipment be installed by the utility or the OEM?
I want to avoid that answer. No, I cannot. The answer is yes, if you know what you're doing. Okay, and that's a big if you know what you're doing. I know it looks easy. You look at the manual. It's easy. Just take the sensor, put some glue on, put that on the core, and there you go. It's a lot more complicated than that. If you know what you're doing, it's very simple. If you don't know what you're doing, it's very difficult. So I always say in my training courses, because I always get that question during the training courses, and the real answer is there are 3 or 4 different ways to install the air gap sensors correctly. There's a million ways to install it incorrectly. And in my 25-year career, what I've come to understand is our customers are very creative. They can come up with all kinds of ways to install incorrectly. And I've seen sensors installed on the opposite side. I've seen sensors installed like this. And I have a case where they had a pole temperature probe. They installed 2. And usually what you do, of course, is you install one at the top and one at the bottom. Well, these guys installed one at 0 degrees and one at 180 degrees. It's looking at the same area, so the temperature is going to be the same. Yep. So, somebody didn't read the manual. So, what we always recommend, just to be serious for a second, we always recommend. Let's say you have a power station with 4 units and you want to install it yourselves. Please ask our service department to at least do the first one. If possible, let them do all 4. That way, you'll be sure that it's installed correctly. But if you want to do it yourselves, at least let our team go in and show you how to do it, where to install, what are the do's and don'ts. We're running cables through 18 kV. You have to know what you're doing if you don't want to kill anyone. If it's a very harsh environment. There's all kinds of EMI around, high temperatures. There's all kinds of things going on. It is very easy to install so that it works correctly, but you do have to know what you're doing. So personally, I would ask you to use our service department to install all of them. They know what they're doing. It will be done efficiently, quickly, and you can be sure that it's going to work correctly. If you do it yourselves, maybe it'll work correctly, maybe not. And if you want to start gluing stuff inside the unit and it turns out that half of them don't work, I'm sure nobody will be happy, including us. So please make sure that you do everything you can to install it correctly.
There's another question here. Why would the pole faces heat up because of uprating the unit?
Well, the reason for that is if you increase the turbine output, in fact, in many places, the water is producing the maximum amount of megawatts based on the turbine design. So in many cases, they can't put more units, but turbine technology has improved. So in some cases, they can put a new turbine in, get an extra, 3, 4, 5% output, which makes it that you will increase the electromagnetic stress between the rotor and stator 5 or 6, 7%. So that extra power will have a tendency to heat the components. Now, if in addition to that, you have a stator that's not round, it means that each pole, as it rotates, will be subjected not only to a higher level of flux intensity, but a varying level of flux intensity. And that variation can create eddy currents in your laminations, and it's also on the pole faces, in some cases, the amortisseur bars. And all of these can heat up way beyond the specifications of the materials that you have and will cause issues. We've been involved in a few cases where they suspected they had these issues. One was in the Maritimes here in Canada, and they were expecting to measure something like 65 or 70 degrees C on the pole faces, and we saw levels up to 105 degrees C. So they had uprated the unit and they had issues which we were able to document. So increased electromagnetic strength, in addition to incorrect symmetry between the rotor and stator, can and will produce excessive heat on the pole faces and other components of the rotor as well.
I guess that will be it for today, Andre.
Okay, well, thank you all for joining. Thank you for participating. Thank you for all the wonderful questions. I hope it was interesting. I hope the video was fun. The session will be on our YouTube channel for those who want to look at it later on. We invite you to subscribe to our YouTube channel. Don't forget to click on the bell so that you can get notifications of new content on the channel.
Also, don't forget to write your comments or questions at the bottom of the page after this session. We will answer them during the next Q&A session. The videos will remain permanently in our channel, so you can listen to them at any time in the future.
And again, if you want to contact us directly by email, please do so. You can reach me or one of the members of my team at the email diagnostics@vibrosystem.com. If you have any technical questions about installation, about number of sensors, about maintenance, or what, you can contact our service department at service@vibrosystem.com. And if you have any questions about products, history, if you'd like to have a business manager come to visit you to discuss your monitoring needs, please feel free to send an email to sales@vibrosystem.com.
You can also contact us via the comments below, or via our LinkedIn page, our website, or via Facebook.
Okay, so thank you all for joining us. Make sure you check regularly to see when our next session will be. And until then, thank you all and be safe.
Take care, be safe, see you next time. Hasta la próxima.
Take care.